4-point functions, 4-point amplitudes. Two particles come in, two particles go out. We'll just do tachyons. We put states like P tensor the ghost, and then we convert it to correlation functions on a sphere with insertions which can be either C bar e to the I p x, and at the fourth point, instead we put just e to the I p x, the Z4 bar, and integrate over. And as I was mentioning last time, what you could actually do is to just put at every point something like C plus the Z, C bar plus the Z bar, e to the I p x, and then decide later where to integrate, if integrate over Z1 or Z2 or Z3. Once you insert these sort of things in the correlation function, the amplitude you get is a closed form in the positions, and so you can deform the integration contour freely without changing the answer. But anyway, I invite you to do it. I mean, it's a very small extension of the calculation we're doing now, because at the end, the correlation function of the e to the IPX factors out, and we are only just trying to understand what is the 4-point function of sort of product as I goes from 1 to 4 of C of Zi plus the Zi, C bar of Z bar I plus the Z bar I. So I invite you to check that this is a closed form in C4. I mean, that times the momentum. Okay. So you can imagine here this C4. I cannot draw C4, I'm not good enough. Then there is an orbit of conformal transformations in it. So there is this C4, I'll draw it like that. Then there are some orbits which are sort of generated by SL2C, by transformations like Z goes to AZ plus B over CZ plus D, which are global conformal transformations. And you're just trying to pick a slice of these gauge orbits, standard stuff. And one of the slices, I fixed 3 points and integrate to the fourth. Which of the points I'm doing this for crosses the same gauge orbits, and they are just different contours, so it can be deformed into each other. And I'm integrating a closed form there, so the answer will not change. Okay, so I think last time we pretty much wrote down the correlation function. So it looks like this. So before integrating, sorry, so this looks like that. I have a prefactor in front which only involves sort of the weak contractions between the fixed points, which are not integrating over, which is something like Zi minus Zj to the 2 plus 2 pi dot pj. And then inside the integral, we have the product, the contraction between Z4, the fourth vertex operator, and the other ones. Does this formula look reasonable? So This 2 came from the CCC correlation functions, and the rest comes from the vertex operators. Now, and we're supposed to integrate over the whole complex plane, perhaps minus the locations of the other points. So this is reasonably integral. Let's do some checks. First of all, this is supposed to be an integral over a sphere. Nothing bad was supposed to be happening at infinity. Let's just check that for sanity. How does this behave at large Z4?
It depends on what 2 times before the pi is.
Yeah, so it's something like Z4, the 2 P4 times the sum of the pi's. But my momentum conservation, which I of course forgot to write, this is the same as Z4 to the minus 2 P4 squared, which is Z4 to the minus 4. And this is good because the measure the Z4 bar over Z4 to the minus 4 is actually the same as the 1 over Z4, the 1 over Z4 bar. So this is treating infinity as if it was any other point. So the only problematic situation is when Z4 hits other points. When is this convergent as Z4 approaches Z? So some condition on this 2p4.pi. How negative can it be for this to be still integrable?
Is larger than minus 2 or something?
Right. Locally, I have an r dr in the measure. And so if I divide by r squared, I get 1 over r, which is the logarithmically divergent. So I need this to be greater than minus 2, which means that P4 plus Pi squared has to greater than or equal than 2. And so as I was mentioning last time, we can just do the integral here and then analytically continue to general P's. Or we can try to deform this integration contour a little bit. So this integral is done. So this is just an integral over the complex plane. But sometimes it's interesting to think about this as an integral on some cycle inside C2, where C2 is parameterized by Z4 and Z4 bar. So here we're essentially integrating over this expression. This expression is just a polynomial, just a function of Z4 and Z4 bars in principle. It can be analytically continued to a situation where Z4 is not complex conjugate to Z4 bar. So you can think about this as a contour where Z4 bar equals Z4 star inside a more general configuration space. And then you can try to deform this contour without changing the answer. You can make it spiral a little bit as it approaches the eye or something like that to make it convergent. I want to mention it because it's actually quite a useful technique in some situations. But anyway, let's not get lost into that. Now, we want to compute this integral. How would we do so? Well, actually, I kind of wanted to mention this also because it's an interesting question. How do I compute this integral? Right? To simplify the expression a little bit, it's useful to set the zi's as some special values. So it's not difficult to check that by a transformation, you can define a new variable t, which is z4 minus z1. It's called the cross ratio, z2 minus z3 over z4 minus z3, z2 minus z1. This is called the cross ratio. It's invariant under conformal transformations of the plane. And if I express this integral in terms of the cross ratio, all the z dependence drops out, as it should. So you can also write that A4 is an integral, again, on the complex plane, minus 0 and 1 of t to the 2p4 dot p1, 1 minus t to the 2p4 dot p2. How would you possibly do this integral? Anyone here feels?
There's like a relation when I shift t by 1 or something, and then I could, I don't know.
This will just give you the fact that it's invariant on the permutation of the p's. Like it will exchange the role of p1 and p2. You could also do t to 1 over t. It will exchange the role of p1 and p3, I think, and so on. So there are two strategies you could use. One is to use a kind of a Feynman parameterization. So you could say, okay, what if I write t minus t0 squared as e to the some power as an integral of e to the s t minus t0 squared from 0 to infinity, and then I put a power of s. This kind of works. You can do that. You plug it in. You do it for each factor. Then you get an integral which is Gaussian in t. And then you're left with a bunch of integral over these s's. Okay, not immediate, but doable, definitely. I wanted to mention another cute technique, which is to do indeed do this fancy deformation. So you can try to treat t and t bar as independent integrals, as independent integration variables. So if I can draw a picture, here I've put the t and here I put the t bar. It's like we're trying to do an integral like that. Just writing the real parts. But integrating as an expression on this diagonal. And what you can do is to deform the diagonal to, morally speaking, some product of integrals that live, of integration terms that live only in t or in t bar. There is a technology to that. You can sort of, it's a bit tricky because the things you're trying to integrate are not single valued. So you're trying to do integrals like this. So you're trying to rewrite it as a sum with some numbers and some choices of cycles. And these sort of integrals are called beta integrals, and we know how to do them. So the tricky thing is to figure out how to possibly decompose this integration where t is equal to the bar dagger. to a basis of possible contours for this. But there is a technology. You just need to learn how to intersect contours and to do intersection theory. It's actually a very cute technique. But anyway, let me just write down the answer. Okay, so it's a ratio of products of gamma functions. It's called the Virasoro-Shapiro amplitude. Okay. It's perhaps better to write it in terms of Mandelstam variables to make it look like a more conventional expression. But it's never going to look conventional. But okay. So this is supposed to be the 3-level 4-point amplitude in string theory, of 4 tachyons in string theory. Can we study the properties of this? So first of all, it has no cuts. So remember okay, I don't know, maybe I should step back. What do you know about the analytic properties of S matrices? It's really a question. I don't know what you have seen about S matrices and how do they behave as a function of the momenta. What properties of analytic properties of S matrices come to your mind? If you have seen anything. If you haven't seen anything, just tell me so that I can give you some.
So, is there some law that like bounds like single particle states propagating correspond to poles and multi-particle states to branch cuts or something like that?
Yes, that's true. So typically the S matrix has cuts or singularities which are required to get unitarity to work. And the discontinuities across these cuts have to do with in things that can propagate in the intermediate channel. So if you have some 3-level process, well, clearly this has something like 1/p² plus m². And so you're going to get a pole when p² is on shell, where the total, the S channel momentum is on shell. If you have a more complicated diagram, something like that, you don't get a pole, because there is an integral of some loop momentum. You get like a smearing of poles over a certain region. The smearing of poles becomes a cut. So you have a cut. And the cut is happening just because if you're asking what's the possible momentum carried by 2 particles, well, that's a continuous thing. A single particle carries just, have a specific value of p², but 2 particles have a generic value of p² above the sum of their masses. So does this have cuts? What are the analytic properties of the gamma function?
Integers?
Yeah, that's right. Poles at 0 and at negative integers. And otherwise, smooth. So this thing has no cuts. It has poles. It has poles when, say, -1 minus s over 2 is equal to 0, -1, -2, -3, etc. Which means that s is -2, 0, 2, 4, 6, 8, and so on. What does this remind you of?
Is this the masses of the strings? Or something?
Yes, that's right. So the theory has a tachyon, a graviton, and other massless states, and a tower of massive string states, whose m squared is an even integer. So we are encountering the fact that the only way this integral can get divergences is because something is propagating for a long time. Something is a particle, and we see the corresponding poles. And you can do now, you could in principle say this, I take the residue of A4 of S at S is equal to 2n. This is going to be some function of the other of t. And you can totally ask, okay, is this function compatible with the fact that actually scattering a scalar or a graviton or whatnot? And yes. So more precisely, this function looks like something like this. See, when you compute the residue here, one of the gamma functions dies. The other gets evaluated as some integer. You get some factorial, nothing interesting. And then you get a ratio of 4 gamma functions. But because s plus t plus u is 0, the arguments of these gamma functions actually end up differing by integers. And so there is a gigantic cancellation. So this actually becomes a polynomial in the momenta. So this strange-looking function, this kind of strange-looking scattering amplitude was originally discovered by people who wanted to sort of build nice functions which had beautiful poles in S, T, and U. And they landed on these sort of expressions. So you can see that, the coefficient, the residue of this point is just a number. The residue here is quadratic in the momenta, and it looks like an exchange of graviton. This is quartic in the momenta because there are spin 4 particles at that mass, and so on and so forth. Okay, so poles, good. It's just this compact expression which by itself manages to have all the poles in the S, T, and U channel. It's kind of weird because sometimes you can reconstruct a function from its poles sometimes, write it as a power series in some regime. You can sort of write something like fn of t over s minus 2n or something like that. If you do this sum in the appropriate regime, this will actually give you that. But you could also expand it in the T channel and the U channel. So this is really weird because it's like the same function can be reconstructed just by summing over Feynman diagrams that look like this, or summing over Feynman diagrams that look like this. It was called channel duality, and it was actually something which, before string theory came, people were looking for, and then they landed on this. And then they discovered string theory at some point out of this in a way that I don't pretend to understand. Okay, now I want to show another feature of this scattering amplitude. I want to ask what happens at large energy. Suppose we take these tachyons and throw them at each other very hard. So how do you study the behavior of the gamma function at large values?
Can use like Stirling's approximation.
Yeah, Stirling approximation. How does it look like?
There is like a square root of n and e and over e to the n.
Let's write down the things that matter first, and then we write then the rest. What's the biggest thing?
Like z over e to the z or something.
There's e to the s, e to the z log z. That's right. And then we can say something like there is a minus z, and then there is a what was it? 1/2 log z, and then there is probably a log of square root of 2 pi, and then there is a I don't remember it 1/12 z. Anyway, there is a asymptotic series expansion for logarithm of the gamma function. I only care about that. So this turns out to behave as e to the minus s log s minus t log t minus u log u, if s, t, or u are large. So it goes to 0 very fast. This is very different from what you would see in a theory of gravity naively. If I take a theory of gravity, in perturbation theory, I scatter 2 particles out of each other. The intermediate channel is going to grow. If I fix on a specific term of this sum, it explodes at large transverse, a large t. So if you sort of try to do it's like we're trying to discover quarks in a proton. We just throw something at the proton in this deep inelastic scattering regime, throw an electron at the proton or something, and try to see if there is structure. Here it tells you if you try to throw something at a string to find structure, you find the fluffy marshmallow. So the amplitude starts going to 0 very fast. This is related to the fact that there are no UV divergences in loop calculations, actually. So normally in theories of gravity with a finite collection of particles, scattering amplitudes grow with energy, and at some point they go beyond 1 and you're dead. And in string theory, they sort of there is a conspiracy that comes from this infinite array of particles that makes the amplitude go down again.
Is this somehow related to like UV IR mixing, that the string gets bigger as I throw energy or something like that?
Oof, that I don't know. Maybe. I don't know if there is. We can talk about UR mixing in perturbation theory. There is definitely fluffiness, and also the geometry really disappears at short distance scales. So what happens in string theory is when you try to probe short distances, the gravity is not a good approximation. You don't have space-time. And actually, next lecture, we're going to see some examples of how the geometry is not really something that works that we expect in string theory at short distances. Actually, perhaps the lecture after the next. Now, perhaps I should also observe. So I did it for tachyons. If we sat down for perhaps another couple hours, I could have done for gravitons. In a sense, and then I could have taken a low energy limit and discovered the scattering of 4 gravitons out of involving a graviton intermediate channel. So probably I would have to work a little hard to decouple the B field and the dilaton. But still, this is a little shocking because if you sit down and try to do 4 graviton scattering amplitude in general relativity, you're going to spend days because you're going to have to sum so many Feynman diagrams. So the simplicity of this sort of calculations was one of the early hints that Feynman diagrams are a terrible way to do calculations in gauge theories. This observation has taken a life on its own since, and by now there is a big industry in how to, just learning how to do perturbative calculations in gauge theories, gravity, without Feynman diagrams, but instead using some smarter techniques. Because, at some point, what is the simplest example? Maybe is it 6 gluons, 4 gluons? I can't remember. 2 to 4. Anyway, at some point, people computed some scattering amplitudes of 6 gluons in Yamil's theory. And, after you sum the Feynman diagrams, you get an expression which is pages and pages long. And then somebody decided to patiently try to simplify it. It was a rational function. It was a 3-level thing. So just a rational function that you couldn't write in a piece of paper. And at the end of the simplification, ended up with a formula that is like, this long, the Park-Taylor formula. So, right, definitely there are better ways to do Feynman diagrams, to do perturbative amplitudes in Feynman diagrams. Another thing that came out of these calculations, see this cute little trick I mentioned it partly because there are some general principles behind it. At some point later on, maybe we'll look at open strings scattering amplitudes, and we'll find expressions which look like just this. And people realize that this is kind of a general pattern, that you can take gravity calculations and split them into two, and each half is a gauge theory calculation. And so again, people learn to use, there is sort of a whole industry on how to double up gauge theory amplitudes to produce gravity amplitudes. So definitely you can learn a lot about perturbation theory just by staring at these expressions.
So what statements you make about scattering of 4 gravitons? Would it still have some poles like this, the poles at the same points? How did?
Well, no, scattering of 4 gravitons will only have poles at s equal to 0 because they are exchanging no, sorry, you mean scattering gravitons in string theory? Yes. It will be a similar expression. There will be a bunch of some polynomials in S and T and U. But right, you'll have the same pattern of zeros and more complicated residues.
And what about high energy scale?
And same at high energy, so this will not affect. Again, you'll have some polynomial in S and T, but it loses against the exponential decrease.
Mm-hmm. And what's the argument? Why is this persisting like higher order terms, loop calculations? Because this is 3-level, right?
This is 3-level, absolutely.
So why divergences don't come back in like loop level?
So the divergences at loop levels usually come from bad behavior at high energy at 3-level. One could try to make this statement more precise, but intuitively, sort of, you can imagine, it's not a good way to say it, but you can imagine sort of first computing these and then gluing 2 legs together. Not a great statement, but you can improve on that. So having a 3-level amplitude that grows polynomially is an indication that when you try to integrate over loops, you're going to try to integrate polynomials and you diverge. I mean, at the end, the absence of UV divergence can just be argued from the fact that in the moduli space of Riemann surfaces, there are no points where the integral diverges in a way that is a UV divergence. All the locations where things can diverge are the boundaries of the space, and the boundary of the states always look like something has propagated for a long time. So all divergences are IR divergences in conventional string theories, at least. Sometimes you get in. There are some weird situations in it is in anti-de Sitter space, where you can get poles in the middle of the integration contour. And those tend to have some very subtle meaning. But they're not expressing a field theory V divergence. They tend to express stringy issues, like I have a string which does not want to stay small, but is happy to become very large and reach the boundary. This different type of divergence it gives you this pole, but you never get things that you can interpret as a V divergence.
Can you explain a little more why Feynman diagrams are so bad for this? Like, is it related to that in our computation now we had something that was gauge invariant all the time? Or?
Oh, why string theory gave a simpler expression is just because it was not a sum of Feynman diagrams. If I had tried to chop it up into Feynman diagrams, like do string field theory, I would have gotten the same horror at intermediate stages. But why is Feynman diagram so bad for computing these things in gauge theory? I think it's just because let me see how to say it properly, but when you study gauge theory, one way or another, you're just adding by hand a whole bunch of degrees of freedom they're destined to cancel out at the end of the calculation. And they do precisely that. They cancel out at the end of the calculation. And in the meanwhile, they do horrible things because they're not as nice as the original gauge fields you want to study. So a longitudinal photon, a longitudinal gluon, or a ghost are just not as nice as a transverse gluon. Yes?
Have people sort of seen cuts in the one loop amplitude? Like, can I actually integrate the sort of one loop expression for this and find?
I think so. I'm not super familiar with those calculations, but people did compute 4-point graviton scattering at one loop. So I think so. That presumably was all the cuts.
So what I remember is there's some sort of integral, sort of fundamental region of the torus moduli space or something, right?
Yes.
And I don't know how to like see the cuts because I would have to sort of perform the integral.
You want to see how to see the cuts, sort of string theory perspective. Okay, let's see if I can get there. I think I would have to think about it a little better, but I mean, expect it'll come from the original parameter space where the torus. So I'm looking at something like this. And then there is a region of parameter space where these two tubes become long and thin. That would be my guess for the dangerous region. So that means that simultaneously the torus is becoming long, but two punctures are also colliding. So it's a codimension 4 location. And I mean, in practice, that will give you the same sort of 1 over product of two propagators integrate over an intermediate loop. So I would expect this to give you the cut by the same mechanism.
So it's not like I have to sort of integrate the whole thing. I can just take some limit in moduli space, extract the cut from there.
No, I seem to remember that was it Sen that recently, not long ago, was proving unitarity of the perturbative string theory scattering matrix. I had to check the literature. So I assume people have checked unitarity of the perturbative matrix of string theory, but I cannot promise. So it should be possible to show that as you try to take the unitarity cut, you get contributions from regions where the Riemann surface is splitting into pieces, and that you're summing over intermediate channels. Yes. Okay, so what I wanted to discuss next lecture is a little bit how to discover that these scattering amplitudes contained inside things like gravitons without having to do a whole bunch of scattering amplitude calculations and comparing those with scattering of gravitons. So suppose I asked you, okay, you have the scattering metric in theory. How do I write down an LONH effective action? So abstractly, the procedure is, well, you take your scattering matrix, you write down, you figure out what are the scattering states, you write down a generic Lagrangian for the low-energy degrees of freedom, and then very patiently you compute amplitudes with that Lagrangian and adjust the couplings until they match the scattering matrix. There's matrix. We could do that. It would be very tedious. And there is an alternative way, which I would like to discuss. And perhaps as an introduction to that, I wanted to sort of observe, remind you of a fact about conformal field theory. So suppose that you wanted to deform our free theory describing motion of strings in flat space-time. So we have our action. Suppose I want to add an interaction. I want the interaction to preserve, to still be compatible with what we're doing. In particular, while invariance was very important, conformal symmetry was very important. How do I make sure that this interaction preserves while invariance, preserves conformal invariance? So how do I make sure that this, let me just write the z dependence, that this is invariant under local coordinate transformation. Z goes to some function of z prime. Or if you want, I should ask you, how does this transform if I do the transformation? Then let's check if it stays the same.
I would have to compute the beta function and the tree level.
No, just easy, just easier. I just write this expression. How does it transform under coordinate transformations? How do we want it to transform under coordinate transformations so that it is invariant?
There actually would have to be some density, right? That has the correct scaling.
So I can write I of z bar, the z bar, and I can say I want this to be the same as I of z prime bar, the z prime, the z bar prime. And I can perhaps move this to the other side. So this is telling you that this I is a primary operator of dimensions 1, 1. And if you remember, this under the state operator map, this means that I is killed by Ln, and also L0I is I. Okay. These were the same conditions I had for physical states in string theory. Curious. Let's push it a little farther. Can you imagine a situation where an interaction does nothing?
Integrating identity or something?
Okay, the identity actually shifts the action a little, but fine, it's almost nothing. But when is it? When does an integral vanish?
It's total the derivative.
Right. So if I was equal to del J, I would just would do nothing. So that means that the state. So if I happens to be, what is the derivative? The derivative is actually L minus 1 acting on things. So if I is L minus 1J, this does nothing. But actually, I can do more general thing. I could have put any function of z in here. Anything that is a total derivative would fail. This thing actually happens to be L minus n on J. So the things I can do to deform a worksheet theory are primaries which are not descendants. But that's literally what the same as saying physical states modulo null states in string theory. So there is a strange correspondence between interactions that I can put on the worksheet, not on the starting space. I should call it deformations of the worksheet theory. I want to correspondence to states, string states. Okay, so if I do these, things seem fine. Now, can things go wrong? Suppose now I have a nice primary which is not a descendant and add it to the action. Could I still have any problems? And where would they come from? So how do you call a situation where I do something that classically is fine, but might be problematic quantum mechanically?
Anomaly.
An anomaly. Yes, so you could have an anomaly. Anomalies come essentially from the fact that I might have a non-trivial OPE with its divergent OPE with itself. So when I try to define an e to the integral of I, which is 1 plus integral of I plus integral of I squared over 2 and so on, this might break down because I have two i's, I'm integrating them both on the worksheet. When they meet, they diverge, so I can have a trouble. So in practice, what happens is if I try to do a scale transformation on the theory, call it the delta scale, on the modified theory, I might actually find that after I regularize and renormalize and whatnot, my theory will have changed, my deformation will change. So the anomaly is that I have a theory which is scale invariant, but if I deform the theory a little bit and I do a scale transformation, I don't stay. I move a little bit. Like, I don't know, in Yang-Mills theory, the gauge coupling changes a bit if I do a scale transformation. So this thing is usually called the beta function. The beta function tells you what's the infinitesimal change of the couplings as a function of the couplings. It's a vector field in the space of couplings. And if we have a beta function, there will be trouble. I'll say this delta is really a function of I. Okay, it's actually polynomial in the shows of interactions. And so, can I say this properly? Right, so there might be obstructions to doing a deformation. And these obstructions are polynomials in the deformation. What happens on the other side? I mean, could I still have this sort of correspondence? So suppose I have a quantum field theory, and I tell you, this state is fine. This particle in this state has this particular energy. Could there be a situation where if I put two particles, now the energy is not the sum of the energy of two particles? Yeah, quite common. It's called an interaction. So we'll learn how to convert information about the beta function to information about how the string states interact. So we'll sort of think about this as a situation where I have added one particle, two particles, three particles, and so on. And I'm trying to make sure if things are still consistent. I'm trying to create a coherent state of particles. And when I have interactions, creating a coherent state of particles means finding a solution of classical equations of motion, which might be nonlinear. And the linear part is sort of the on-shell condition. But then there are nonlinear parts that tell you, oh, wait, you need to be careful when you try to create this coherent state. The interactions are going to modify the way the coherent state is built. You need to solve the classical equations of motion with all the nonlinearities. And so we learn how to get sort of the classical equations of string T of the target space fields out of beta functions. Okay.
Could you overview what did you do on that board? I'm a bit decoupled. So basically.
I will review it from scratch next time. So, but yes. So I'm trying to argue. So first, I argued that there is this curious correspondence between deformations of the worldsheet theory and string states.
Yeah.
Single particle states of the string theory. Then I reminded you that the deformations have a nonlinear structure of some sort that tells that if you try to deform infinitesimally at the second order in perturbation theory, you might have to correct your deformation. This is called the beta function. The beta function tells you that you need to be careful when you deform the theory. If you want to deform the theory and keep scaling invariance, your infinitesimal deformation might have to be modified at each order in perturbation theory. If possible, you might not be able to do so. But, And I'm just saying this nonlinear structure will compare to the nonlinear structure on states. So whenever you study a quantum field theory, you can ask, how do I build a coherent state, a superposition of many photons, say? And if I was in free electrodynamics and I say I want to build a coherent superposition of photons, I just take a solution of the linearized equation of motion, they're just equations of motion, and I sort of exponentiate it. I take a creation operator for that photon and I exponentiate it, and I get a classical configuration of the electromagnetic field. If I try to do the same with gluons, I would get in immediate trouble. If I take a gluon state, a gluon creation operator, and I try to exponentiate it, interactions would tell you that this is garbage. This is not a good state. The correct way is to look at the classical equations of motion, a solution of the classical equations of motion, and exponentiate that in a sense. We can discuss that more in detail. But I'm anticipating there's going to be an analogy between the two things.
So the reason why I get a coherent state is because I have like an integral over d squared z of the interaction, so I have many sort of...
Yes, many places where you can collide. So Now notice I was using the CFT language here. So this variation of beta function, the variation of scale invariance is like, okay, it happens. If it happens, it happens. I don't have a conformal field theory. But on the string worksheet, conformal invariance is gauged. So a failure of having a beta function is a very serious problem. It means it's really a gauge anomaly. And there are nice ways to describe this. I can perhaps show them later on. And it's just a beautiful thing that when you try to describe these BRST anomalies, they immediately look like equations of motion of something. And then with a bit of insight, you can see that these are the equations of motion of the fields in the target space. The equations of motion for this collection of gravitons, dilatons, tachyons, and so on.
For all the fields or only them? Because I remember, like, only for the massless fields, like what I've seen written.
Yes. Well, it depends on how energetic you feel, meaning in principle, it's possible to take a quantum field theory and add all possible deformations of it, all possible couplings, formally, in perturbation theory. And then in each order in perturbation theory, you can renormalize the whole infinite tower of things. And you get an infinite collection of beta functions, one for each coupling. And formally, these will be the equations of motion of string field theory. So of a field theory which at tree level at least reproduces the scattering amplitude of string theory. And with a little bit of BRST formalism, you can really make this statement manifest that it's literally true that what you computed when you compute the scattering amplitude is some kind of BRST anomaly, which is at tree level at least the same BRST anomaly that you will be computing in trying to look at the violation of scale invariance. And you can try to push this even farther, but at the loop order, it becomes more complicated, though.
Sorry, then are we going to relate these beta functions to the stress energy tensor in some, or?
You could. I mean, one way to define the beta function is that you look at the trace of the stress tensor and you expand it in operators. I mean, so this delta I is, by definition, pretty much the stress of the stress tensor after deforming in the deformed theory. Because the trace of the stress tensor tells you what happens if you do a scale transformation. I just find it more useful to think about it as the variation of your interaction. So there is something called, so it's really a formal perturbation theory. You have your theory, and then around it there is this sort of formal neighborhood which consists of perturbative modifications of your theory. You would like to say like there is a neighborhood of nearby theories, but they're not really theories. They're just doing perturbation theory, like formal theories. And on this formal neighborhood, there is a vector field, which is the beta function. It tells you what happens if you do a scale transformation. And the zeros of this vector field are the theories that remain conformal invariant, which are formally conformal, the formal theories which are conformal invariant perturbation theory. Now, if you actually have a family of theories, it will sort of infinitesimally give you this. So dually is like here, I'm in some string vacuum. And once I identify the deformations, the perturbative deformations as particles I can add on top of this vacuum, I can ask, okay, can I start piling up particles on top of this vacuum to make a different vacuum? One in which maybe there is a big, or a different state, where there is maybe some classical wave propagating through or something like that. And I need to do this in a BRST invariant way, in a consistent way. And the consistency condition ends up being precisely the same as the consistency condition for having a new formal vacuum with a new formal Cauchy theory that describes this new configuration.